Okay, something for scheduling. Our final exam is on a Monday and not a Tuesday. So for our other exam, we did a review session on Sunday and one on Monday. That was cool. Do you guys want one on Saturday and one on Sunday? And if you do, give me some time so I can check with Niels. I'm pretty flexible. So that's a week from this coming Monday, right? 12 days from now or something, 11 days from now. Speak to me. When do you want to do the Q&A?
Early afternoon.
Meaning 4 o'clock?
3, 4, something like that.
Okay, that's one idea. What do you guys want? Who wants midnight? You're not getting me. So that would be Sunday or both days?
I both.
Nobody else is going to come, so I should just have Sabrina in my office, and that'd be great. That'd be great for you.
Maybe a little closer to the evening on Sunday.
Sunday, I don't know. It's up to you. You're more focused in the evening, like 6 o'clock.
Yeah.
We can do Sunday at 6, Saturday at 4. Then. Does that sound like? Okay. Somebody shoot me an email so I don't forget to reserve rooms, okay? Somebody got a phone out? I don't bring mine. Cool. Hopefully be Niels on one and me on the other, but maybe he's out of town. I should be here. So, okay, so with that highly democratic process out of the way, let's get back to compact sets. So we're focusing on sequences. We did a really nice review of them on Tuesday, and then we introduced this new notion called a subsequence. So if you have a sequence, and then you have a selection of indices that are strictly increasing, so then it marches off to infinity, just like n equals 1, 2, 3, 4, 5, 6 marches off to infinity. That indexed set of vectors is called a subsequence of xn. And so the way we are using them is in the notion of compactness. So a set C is bounded if I can contain it within some finite open ball, okay, so sufficiently big. And then we proved, we just constructed it. If a set C is unbounded, I can always find a sequence of points that I build from elements of C such that the norm of the element of the sequence is strictly increasing. So I start with an x1. The set is unbounded, so I can find something with a norm that's bigger than the norm of x1 plus 1, and then I just do that by induction. So these points are always far apart from one another. And hence, if you choose any subsequence of that, and of course the whole sequence itself is a subsequence of itself, any subsequence you choose, it can never be Cauchy. The terms can never be getting close together. Hence, it can never have a convergent subsequence because being Cauchy is a necessary condition for a sequence to converge. So if you just use our handy inequality, the norm of x minus y upper bound is lower bounded by the norm of x minus the norm of y, its absolute value, you get that how close together are any 2 points in a subsequence? Well, they're going to be at least the size of ni minus nj apart. So you just prove that from this right here and the handy inequality. So when sets are unbounded, if I just choose a sequence, I can always construct a sequence there such that it has no Cauchy subsequences. Okay, so with that as preparation, then we said a subset of a norm space is we just use the word compact. There's actually a couple of different notions of compact, and the one we are using people also call sequentially compact. So for us, it's one definition of compactness, and it's this one involving sequences. A set is compact if every sequence constructed with elements of the set has a convergent subsequence with limit in the set. Okay, you can't construct the sequence from C and have it converge outside of C. That's cheating, okay? You can't do that. It has to have the limit inside of C. Okay, so it doesn't mean that every sequence you build in here is converging, but you can always then make selections of a subsequence and build one that has a limit in C. Okay, so with that definition, we get that if C is compact, that it has to be closed and it has to be bounded. Okay, so it has to be closed because we see that C has to contain its limit points. And we know being closed is the same as a set containing its limit points. And if we're going to have all sequences have a convergent subsequence, then every sequence must have a Cauchy subsequence. And we just saw that if the set is unbounded, I can always build a sequence that does not have a Cauchy subsequence. So we get being closed is necessary and being bounded is necessary. So those compactness implies these two properties. The converse is false in general. But if your norm space is finite dimensional, then they are equivalent. Okay? If X is finite dimensional, closed and bounded implies compact. And this was our divide and conquer argument with the beautiful Wikipedia picture. Okay? So if it's finite dimensional, closed and bounded implies any sequence we can construct a convergent subsequence. And our proof had kind of two parts. If the sequence only has a finite number of distinct elements, then at least one of the elements is repeated an infinite number of times, and it was easy to construct a constant sequence. That clearly converges. And then if the set had an infinite number of distinct elements in it, we could just divide the set in two, and at least one half of the set has to have an infinite number of elements, and then we divide that half into one of those halves, and because of finite dimensionality, we crunch down to an ever smaller cube, hypercube, and we get a converging sequence. Okay, so that's really important. Finite dimensional compactness is equivalent to closed and bounded. And then compactness always implies that, but in infinite dimensional norm spaces, there are plenty of counterexamples. Okay? Then we had this notion of continuity. You're playing with this in your homework. We have a function that takes vector space X to a vector space Y. We assume that we know how to measure size in each of them, so we have norm spaces. We say the function is continuous at a point in its domain if given any approximation error, no matter how small, I can find a positive delta such that as long as X is within delta of X0, f of X is within epsilon of f of X0. And so you can write that in terms of balls if you wish. If you do it like this, you see the norms explicitly. And you remember that, X and Y may be very different spaces in general, like Y we're going to take to be the reals in a little bit. Okay, and then in your homework, what you're proving is that a function is continuous at a point if and only if, whenever I have a sequence in the domain of f in x that converges to x0, I have the corresponding sequence in y converging to f of x0. So this is yn equals f of xn. That's a sequence in the range of f. It's converging to f of x0. So it's if and only if. So that means if the function is discontinuous at x0, I can build a sequence in the domain that actually converges to x0, but the image sequence does not converge. And when we had the picture with a jump, we just saw that we could take things getting closer together, but the sequence up here never got close together. Okay, so that's the intuitive idea. And so sequences are these magic things that can be used to characterize closed sets. We use them to define compactness. We can characterize continuity. So it's a tool that lets us connect these properties together. And as engineers, they're important because we have iterative processes to compute solutions to algorithms. Okay, that's my summary, and I'm sticking to it. Questions on the points covered? Please.
Unbounded sequence. Why do we choose one arbitrarily choose?
Make sure I've got the question. So on these, when a set is unbounded, why do I do this or how do I do this?
Why do you choose one?
Oh, here, 1? Yeah, that just, it doesn't matter. I could choose any positive number. Yeah, it's just 1 is very convenient. But you could put 100 here, or you could put 0.00001, and then the elements in the sequence can never get closer than whatever constant value there, so they can't converge. They can't. That's just 1 is just a convenient bound. Good point. Others? Little small things that maybe bugging you, keeping you up at night? No? Okay, so before we get into the main thing, then I'm going to have a little thought, not exactly experiment, but a thought process. So an aside. Okay, so here's the context. F is continuous at x0. I have a sequence that converges to x0, then f of xn converges to f of x0. Question I'm going to write down. Suppose I have a sequence and I know that f of xn converges to f of x0. Can I say anything about this? Are they connected the other way? Okay, I'll write it down just so you've got it, okay? Aside, so we have f takes x to y continuous. Let's just do it everywhere. So there's no problems whatsoever with continuity. We have xn in x, and yn is defined to be f of xn. Suppose that this happens. Does there exist x0 such that xn goes to x0 in whoops, what happened? Got scared. Timid sheet of paper. Okay. Okay, so I take a sequence, I apply a function to it, and I get something that's convergent. Does my original sequence have to have a limit? Be Cauchy, be anything. Can I say anything about that? Or
No, not in general, unless, I think, like, if you just take the function 0, right?
Yeah.
It doesn't do anything with the input, that's convergent, but. Yeah.
Exactly. Okay, so we have one answer saying, thank you for playing. Okay, so let's just draw the picture of a counterexample. But then once we understand this, this is really the underlying idea for proving that if you have a continuous function on a compact set, minima and maxima always exist. Okay? You got to think about that. That's pretty hard because any arbitrary function, if the set is compact, I can prove that it achieves its supremum. I can prove that it achieves its infimum. Now, I can't compute them maybe, but I know it exists. That's kind of pretty powerful, right? So let's just see how this little argument goes, and then I'll guide you towards another little thought process, and the Weierstrass theorem will basically fall apart for us. Okay, so here's my function. Oh, come on. I'm trying to do it where it's clearly a constant. I got close enough, okay? 0 would be perfectly fine, but it's just more fun to, oh, come on. Delete. So here's my axes, and I'm going to define some set S, okay? So this is F equals constant. And then I just choose an x1 here. I choose x2, x3, x4, x5, x6, x7. I just choose the xk randomly. In the interval, let's just say it's 0, 1, okay? Just for the heck of it. Just choose them randomly. Okay, so then we clearly have yn equals f of xn converges to y0. Okay? There's no problem with that. So this sequence, does it converge? Thank you for playing. Unlikely if we just choose them randomly, it's converging to anything, okay? The image, because you could, once again, you could, as suggested, we could just take f being identically constant. So I just took it to be a constant. It doesn't matter. So the sequence yn converges to y0, but it says nothing about xk. Okay? Xn does not converge. That's fine. However, if this is really the reals, for example, a finite dimensional norm space, and this is actually the closed interval 0, 1, then this subset is compact. Okay? So this randomly chosen set of points is going to have a convergent subsequence. Okay. So then I can find a subsequence of this that has a limit in the set. Okay, so I'm just pointing out, I'm going to build shortly. The function's not going to be constant. I'm going to build a sequence in the range of the function, the image of the function, such that that sequence y equals f of xn does converge to something, and it's going to converge to the supremum of the function. Okay. I'm going to do that by sampling values of xn in a certain way. That sequence is not going to converge. However, if the set I'm drawing them from is compact, it has a converging subsequence. And my function is continuous, so the converging subsequence, when I apply the function, is going to converge to my supremum, and I will actually have proven that the existence of a maxima. Okay? It's awesomely cool. Okay, so I'm going to construct the sequence in the codomain in Y. It's going to give me something in X that doesn't converge. I'll use compactness. I'll extract my converging subsequence and prove what it converges to is the maximum of the function. Cute, huh? That's an intellectually interesting exercise. It's got to be good cocktail party conversation, I promise, okay? You've got to find somebody who will find that argument just completely awesome. Now, if not, you're hanging out with the wrong crowd, okay? That's all I can say. So, yeah, let's just skip down and give ourselves some room. Weierstrass Theorem. Same Weierstrass as in the Bolzano-Weierstrass theorem. So it says this. If C is a compact subset of a normed space X, okay, and, that's an and, F takes C to the reals is continuous, and for emphasis, at each point of C, then F achieves its extreme values. Then I'll write down in symbols what that means. Oh. Okay, so the ingredients, continuous function and a compact set. Continuous function, compact set. I.e., there exists X star, an element of C, such that f of X star equals the sup f of X, X an element of C, and there exists an X lower star in C such that f of X lower star equals the infimum X in C, f of X. Okay. So one of the things we've harped on over and over this term is that in general, sups and infimums may not be achieved. So, excuse me, the max and min may not be achieved, okay? So this is saying the max, there is X star is a max. This is saying X star is a min, okay? So, and says that F has max and mins. Maxes and mins. Okay. So there exists a maximum and there exists a minimum.
Question.
Yes, please.
So F has maxes plural and mins plural? The last line?
Excuse me, there may be multiple points that achieves the same one, like for a sign.
Oh, okay.
Yeah, yeah. No, it's not stated very clearly, or elegantly, I should say. It's not very elegant. Okay, so. Okay, so F has a max and a min. And there may be, not saying there exists a unique X star and X lower star, but, okay. F achieves, let's write it like this. One says that F achieves its max and its min. Okay, that's probably better. Okay. Now, the first thing we should notice here is if we're going to have a point where f of x is equal to the sup and the function is continuous, if f is, mapping things into the reals, then the sup has to be finite, okay? So that's the first thing that we need to establish. Because whenever I take the sup of a function over a set, the supremum, it might be unbounded. So if I just take interval minus pi over 2, I take tangent x, it's not looking good. That function is not continuous. I haven't defined it at minus pi over 2 and pi. Oops, I'll just put it 0 or some random points there, but then it's not continuous, okay? So that's a problem there. So it looks like the compactness, the boundedness and closedness of this 0 pi is going to make the function bounded on the sets. That's the first thing we're going to show. So claim 1, or claim. Okay. F takes C to R continuous and C compact implies that the supremum f of x, x an element of C, is finite. So we're getting down to the end. So this may be our last proof by contradiction. So you can start being sentimental, okay? Proof by contradiction. Let's see if I remember how to formulate those. So I want to do P implies Q. And that's if and only if not P and not Q. Okay, so let's identify P. F is continuous, C is compact. Q, the supremum is finite. So Okay, so that's what I want to show. Continuous, there's an and here. C compact, I get a finite supremum. So I'm going to assume F is continuous and C is compact and the supremum is infinite and derive a contradiction. So suppose the supremum is equal to infinity. Choose a first element in X such that f of x1 is bigger than or equal to 1. Okay, so there has to be at least one element such that f of x is greater than or equal to 1, otherwise the supremum is not infinite, okay? And once again, this could be 10, 12, but 1, okay? And then by induction, choose xn plus 1 such that f of x n plus 1 is greater than or equal to f of x n plus 1. Okay, so I'm building a sequence in the image, in the reals. So this sequence yn is in the reals, so I have yn by definition equal to f of xn is a sequence in R so can yn have a converging subsequence? Yn plus 1 is bigger than or equal to yn plus 1. So it's the same argument we had with the xn plus 1 greater than or equal to norm xn plus 1. Okay? And has no convergent subsequence. Okay? So we get that from our assumption that the supremum is unbounded. Okay? Now these points xn that I'm choosing, they're in C, okay? xn is a sequence in C, and C is compact. So, since there exists, let's call it x tilde in C, and a subsequence x n sub I such that x n sub I converges to x tilde. Oh, come on. Okay, so that's from compactness. Now, f is continuous, right? So we're using let's see what we're using. We're assuming both P and not Q. We're assuming both F is continuous and C is compact, and F is unbounded. The supremum is unbounded. From the supremum being unbounded, we built this sequence that does not converge in the reals. But yet, we built that by choosing points in the domain from a compact set. So it has a limit point in the compact set in a subsequence that we can choose. So now I'm going to use F as continuous. Thus, if I apply F to xn sub I, that converges to F of x tilde as I goes to infinity. Right? That's what we have with continuous functions. If we have a convergent sequence, we apply the function to it, it converges to F evaluated at the limit of the sequence. So that's by continuity. So this is a problem, okay? So we have yn sub I is a subsequence of yn, and yn sub I converges to y tilde, by definition, equal to f of x tilde. Okay? Okay, so we built a sequence in the reals that has no convergent subsequence, and now we just built a converging subsequence from that. That's called a contradiction, okay? Okay, so we now have a contradiction, okay? So this is a contradiction. Hence, P and not Q is false, and we have proved that P implies Q. Okay. Ta-da! A beautiful proof by contradiction. Okay, so we assumed the hypotheses. You write that down. F was continuous, C was compact. We assumed the opposite of the conclusion, the supremum is infinite, and we're able to construct sequences in the real, a sequence in the real that simultaneously has no Cauchy subsequence and does have a Cauchy subsequence. Ta-da! So that's a contradiction. Everybody comfortable with that? Isn't that kind of amazing that you're comfortable with that? If I had done that on day 2, you would have been sit there with your eyes spinning and everything else, no, right? Yeah, don't remind us that we used to be ignorant. Okay, no, I mean, I think it's just practice, repetition, 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 doing drills, drills, drills. Okay, so now we move on in the proof. We change colors so we can tell that we've finished that part. We return to the proof. With the knowledge that F star, by definition, equal to the supremum x in C of x of x is finite. Okay, so I want to build now a sequence that actually converges to F star. How do I do that? From the definition of a supremum. So what does it mean that F star is the supremum of F over the set C? How do I get a sequence out of that? Because sequences are my magic tool when I have compactness. Okay? So if I just have an n bigger than 1, there has to exist an xn in C such that f of xn minus f star is less than 1 over n. Okay, it's the least upper bound. So I can always choose values in C that get me arbitrarily close to that. I just don't know that I can achieve the supremum and actually have a maximum. Okay? So I'm building this sequence in C, but its values can get arbitrarily close to f of x. So I have this sequence, yn by definition equal to f of xn converges to f star. Okay, so given this move, what is the next obvious move to make when you have compactness? And you're starting to get the flavor of this. Yep. And a limit point. And you hope, so I can choose a subsequence here, it will have a limit in C, and you might guess that that limit point is, when you put F on it, is equal to the supremum. Let's just check. Okay? This is the magic here. So now we invoke C is compact. To choose a point x tilde in C and a subsequence xni of xn such that xni converges to x tilde, I goes to infinity. So, question, come on, question. Is f of x tilde equal to f star? Okay? I choose this subsequence, it has a limit in C. Is it true that when I evaluate f at this point, I get the supremum? Why is that true? Because subsequences of converging sequences converge, and they converge to the same limit, okay? So, I let so I have yn I by definition to f of xn sub I is a subsequence of yn, and I know yn converges to f star. Hence, Yni converges to f of x star. And I know that Yni converges to f of x tilde by continuity of f. Put f here, I get here. So Yni converges to this, Yni converges to this, limits are unique, so this one equals this one. That's a tilde. Limits are unique. Hence, f star equals f of x tilde, and we denote now x star. There's a max. Okay, there may be lots of other points in C such that when I evaluate f at that point, I also get the supremum. So this is not unique, but I can choose this as a supremum. And that's it. Okay, let's do it, then we'll do the play-by-play, replay, slow motion. The power of sequences, it's all here. Okay, so the first thing is we prove that the supremum is finite, okay? If not, we can construct this sequence that just marches off to infinity in the reals and it has no converging subsequences. Yet C was compact, it always has converging subsequences, and life got really hard there. We had a contradiction. So now we're using it's finite. So I can then approximate it arbitrarily closely by choosing elements appropriately in C. And so I choose the error to be 1 over n, where n is my index and my sequence. And so I build by definition just to make sure that doesn't look like an ni. By definition, this sequence, yn by definition equal to f of xn, that's the sequence that converges to f star, and that convergence is in the reals. But as we noticed before in our aside, that says nothing about xn converging to yn, okay? Just because f of xn goes to f star, that doesn't mean that the xn's converge to anything. No. Okay. But with compactness, there's a selection of a subsequence of this that will have a limit point in C, and the subsequence converges to that. So we build the sequence based upon properties in the image of F. That gives us a sequence xn, which may or may not converge, probably doesn't. But with compactness, we make a selection of one that does converge. And because yn goes to f star, any subsequence of yn goes to f star. So the yni, which is just f of xni, that goes to x star. Because f is continuous, f of xni goes to f of x tilde. Limits are unique, so this one equals this one. And so we can choose x tilde as a point in C that actually achieves the supremum. Magic, without ever computing it, okay? It exists. I don't know, when I learned this, I was just kind of in awe, okay? I'm not in awe of my proof. It's pretty standard, the proof I've given, but I think it's just uniquely beautiful how you can argue that. Okay. I see a few of you agreeing, a few of you thinking I'm nuts, and a few of you thinking, well, maybe I'll be impressed later on. Okay, that's fine. That's fine. Okay, so that's it for real analysis. Okay, so done. Want to learn more about real analysis, take Math 451. You're super well prepared to do well in the class because you've kind of got the essence of 3 weeks of the course or something. So you just got to learn the other 11, okay? You're coming in with good background. And then if you really want to learn about infinite dimensional norm spaces, have EECS 600 or a math course on what they call functional analysis. Okay, because you usually build your spaces out of functions. That's why that's typically called functional analysis. But there's other ones where you have spaces that are built out of sequences. So you have infinite dimension. Each element in this set that you're talking about is itself a sequence. Think about that, okay? That's kind of cool. Yeah, awesome. Okay, so questions on compactness? You got the essence? Every sequence has a converging subsequence to a point in the set. And from that in continuity, you build everything else. So very fundamental. No? Okay. So let's do the last thing that you guys will keep seeing in hundreds of contexts once you're aware of the words. And it was used in the graduate seminar yesterday. So that was cool. Or Tuesday? Tuesday. So convex sets and convex functions. And so we will end the material for the final exam on page 3 of this, okay? So it's very clearly there. And what you need to know here is super small, but very useful when you get out to be an engineer. Okay, so convexity. What is convexity? So we go back to vector spaces for a little while. We don't need norm spaces to define convexity. So I'm just going to do it over the reals. Set C, C for convex, C for compact, okay? S for subset. C contained in V is convex. If I take any 2 points in C and I draw the line that connects them, it stays in C. So how do you draw the line? Well, you take a parameter between 0 and 1. When the parameter is 0, I'm at Y. When it's at 1, this is 0, I'm at X. And for everything in between, I'm on this line in between them, okay? And the line is not going like this. It's a linear combination, but with very special coefficients. Lambda, 1 minus lambda. Okay, so they're always positive, or non-negative, I should say. Lambda and 1 minus lambda are non-negative. That's called a convex combination. So remember, a set was a subspace if it's closed under linear combinations. A set is convex if it's closed under convex combinations. So it's all kind of similar. So convex, I take any point, draw the line, I don't leave the set. not convex. I leave the set. Okay? So convex, not convex. Yes, no. So I posted these notes. Okay? So that's convexity. We're not going to use this, but it's very much related, so I'll just define it. So if we had a set, we could take its span and build a subspace. If you have a set that is not convex, you just draw all of the lines between all of the points in the set, and you create something called the convex hull. So it's equivalent to taking the all linear combinations of the elements of the set and building a subspace. That's the span. The convex hull, you take all of the lines, all of the convex combinations of points. So yeah, that one's already in there. I'm not adding anything. Oops, I got a whole bunch of new points here, a whole bunch here, a whole bunch here, a whole bunch here. So I close it up under convex combinations and I build a convex set. That's the convex hull. So set, span, set, convex hull. I build the convex hull by throwing in all possible convex combinations. I build the span by throwing in all possible linear combinations. Okay, so it's same idea, but these are very special linear combinations that only look at the line that connects 2 points. It starts at one of them and ends at the other as lambda goes from 0 to 1. Okay, so when you hear about convex optimization, this magic tool, they're assuming the set your function is defined on is convex and the function is convex. And they're slightly different ideas, but very similar. We say a function is convex. Question? Yep.
Would you see that a subspace is convex?
Sure. Yep. So a subspace contains all of its linear combinations, and convex combinations are a subset of those. So by definition, if it contains all of the linear combinations, it contains all of the convex combinations. No? It's good, just putting the ideas together. It's fantastic, okay? So a function, is convex if when I look at the values, I take 2 points, I draw the line between f of x and f of y, the function is always less than or equal to it. So f on a convex combination is upper bounded by the convex combination of the 2 values, x and y. Okay, so things that look like bowls, they are convex. This one, not so much. Okay. Things that look like bowls are convex. Things that look like this, not so much. Ah. Okay. So checking convexity can be painful sometimes. There's really good books on it that give you conditions for how you can check the property. Now here's why everybody cares about convexity. So now I need a norm space again, because I want to talk about local minima versus global minima. So if I take a point in the domain, I'll say it's a local minimum of my function if, when I build a small ball about my point, and I take any other point nearby, so this was positive, f at x star is less than or equal to f of x. So X star is a minimum in this smaller set, so it's local, because that's what balls allow me to do, get things local, okay? And then X star is a global minimum if it works for every X and D, that f of X star is the minimum, okay? So if it works for all of points in the domain, it's global. And if it works for just nearby, it's local. So usually the problem when you're minimizing functions is you get stuck in these local minima, right? Here's a local minimum. Okay? If the function is bowl-shaped, local minima and global minima are the same. There are no locals that aren't also global. So that's the magic property of convexity. So if you have a convex function defined on a convex set, any local minimum is automatically a global minimum. Your algorithm cannot get stuck. Okay? You will never find a locally optimal solution. If you converge, you get the global minimum. Okay, so we'll sketch the proof, but here's the thing. Algorithms for computing minima of convex functions, they're getting to be super efficient these days, to the point that we can run them in real time at a kilohertz rate on small machines. Okay, I don't need a GPU to do it anymore. So there's lots of problems now in engineering where giving an answer to it, you're no longer required to write down closed form solutions and stuff like that in order to use them on your micro embedded processor on a robot. It's enough to prove that the answer to your problem is a minima of a convex function. And then you use tools for convex optimization and you just iterate, and that's it, okay? So we're not there yet that everybody accepts that uniformly as an answer to a problem, but it's getting to be more and more and more true that if you can prove the answer to your problem can be formulated in a way that you're calculating minima of convex functions, that's accepted as a valid solution to the problem. It's a game changer, total game changer. Now, when these algorithms used to be kind of slow, it was just an oddity, a curiosity that you could do that, okay? It was maybe theoretically nice, but not practically important. But the fact that these algorithms are now super fast is what's changed everything. So you'll see lots and lots of seminars now where people are saying, I reformulated it into a convex optimization, and then they basically go like this, okay? And now you know why, okay? It's considered done, okay? Bam, home run. Okay, so that's super cool. There's lots of things that's left to do, but it's really fun math, and you guys will enjoy doing it. The proof here is our very last contrapositive proof, and in fact, it's our very last proof, totally. So we want to show that local implies global, and so we're going to show that not global implies not local. So if it's not a global minimum, it's also not local. So that's what we'll do. So not global, so X not a global minimum implies there's some other point in D, could be very, very far away, such that f of y is strictly less than f of x. And then not local just means I can shrink my point of looking and find a point that's nearby such that f of z is less than f of x. Okay. So I'm going to start out with something that's potentially far away from X, that's smaller, and produce something that's very nearby X, that's also smaller. So not global in price, not even a local minimum. How do I do it? I can take the line that connects X to Y, and I use the fact that the function is convex. Okay? And I prove that if this is true, then every point on that line satisfies an inequality like this. And so then I just choose a point really close to this, and it's done. Okay? So the proof by the contrapositive is super straightforward. So I just say that if I have a point where f of y is less than f of x, I look at all convex combinations of x and y. And as long as lambda is not equal to 0, when lambda is equal to 0, I'm at x. So then that can't be strictly less than f of x, okay? So for all lambda strictly greater than 0, less than or equal to 1, all those points also are satisfy f of z is less than f of x. So I build my convex combination. I use the convexity definition of f. Then I use the fact that f of x is bigger than f of y, so this is strictly less here, but now I have 1 minus lambda plus lambda, and that adds up to f of x, so f of z is strictly less than f of x. So every point satisfies that. And then if every point satisfies that, it's a very quick estimate to choose a delta such that I'm nearby and the particular z corresponding to that lambda is not a local minima. So that's it, okay? So I don't care about the proof, but for the final, no, convex functions on convex sets, if I write down the condition for something to be a local minimum, you're supposed to deduce that it's also global, okay? That's the magic. Local minima are also global. So convex functions, convex sets, they're magic. There's other things that are interesting in here. You can jump to them. Somebody needs to leave, that's fine. This is not on the exam. But just to see how general the convexity can be, any norm is a convex function of its arguments. I take any constant greater than or equal to 1 than finite, I raised any norm to that power, that stays convex. So in particular, you know, if my norm was the pth root of this, I can raise it to the pth power, but I can raise it to any power I want, okay? But anyway, the sums of xi's, so we've been playing a lot with xi squareds. Those were convex problems. If two sets are convex, their intersection is convex. So that's pretty cool. The intersection may be empty, so it's just a convention. The empty set is considered convex. Something like this, ax less than or equal to b, and this is means it's row-wise. So the first row of ax is less than or equal to the first entry of b, etc. So that's what that means, row-wise. That's a convex set. Equality conditions, those are convex. Hence, simultaneous inequality and equality conditions, those are intersections, those are convex, intersection of convex sets. And so this brings us to the magic quadratic program. Okay, so you'll see these all over the place too. Not on your final exam, but you see them everywhere. Yes? Is composition of convex functions convex? Yes. That would actually give you the general result of a norm and then raising to a power. You're absolutely right. So compositions of continuous functions are continuous, compositions of convex functions are convex. So a quadratic program is something on Rn. In general, Q only has to be positive semi-definite. Normally, you'll choose positive definite, but it doesn't have to be. And then you can have a linear term on here as well. So quadratic term and a linear term. And then you put inequality bounds on it and equality bounds. That's called a quadratic program. Why a program? I don't know, okay? Why not a quadratic optimization problem? Okay, but they're called quadratic programs. I think we've been CS'd here, okay? Which is not a bad thing, I guess. So when you guys did the underdetermined case, we didn't put a half here, okay? But you can. So you had equality constraints where there were fewer equations than x's, and you solved the problem, minimize norm of x squared subject to cx equals b, okay? Or y equals cx, etc. So you did the case of a quadratic program without the equality constraints. So that makes it the inequality constraints. You just did the equality constraints. So when you have the inequality, you can no longer write down a closed form solution, but boom, 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 boom. Okay. Now just in robots, where do these type of things show up? So for me, when I'm designing gates and applying torques to my robot, I don't want the feet slipping. That makes the robot fall down. So I'd like to find a problem, for example, where I implement the control input, U, that is as close as possible to my stabilizing feedback, and yet does not cause the ground reaction forces to go outside of a friction cone. So I might do something like this. Make sure the vertical force never gets smaller than 20% of the weight of the robot. I'll usually design the gate so it's never less than 50%, okay? I'm cautious, but, okay? But then I need the horizontal component and I choose my friction coefficient. So 0.6 seems to be something that works pretty well. But I've had days outside where 0.1 was dubious at best, okay? So it depends on, you're walking on ice, or are you walking on concrete, or are you walking on wet grass in the morning? What's the friction coefficient for wet grass? I don't know. But it's not 1, I can tell you that, okay? It's not 1. And so you can take these types of inequalities and rewrite them such that you have a quadratic program. And since you can run these things with, say, 10 variables on a microprocessor and have it be solved in microseconds, even if you're running at a couple kilohertz on your control, microsecond out of a millisecond, that is nothing, okay? You're not getting into your computation overhead. So you just take these constraints and you realize that that absolute value can be written as the plus and minus version of it, and so you just get 2 inequality constraints to impose the absolute value. And you just collect everything, so it's all here, until you get something that looks like this, and this is now the condition for imposing the ground reaction force terms. And then if you wanted to do a quadratic program, suppose this is my feedback that I wanted to be as close as possible to. So if there exists a control that satisfies the ground reaction forces, then I'll choose this one because that'll minimize it. Otherwise, I'll get as close as I can. There's more formal ways to do it, but that's one obvious one. Another way to do it is you put in what's called a relaxation parameter. So just in case you see somebody talking about relaxation parameters, it's no big deal. I can still just do what we've done in class, which is minimize the norm squared. And I'll add in a relaxation because my u will be the feedback I want plus some deviation. If there exists a u that satisfies this, then I can make, I'll do the smallest u, let's see, yeah, I make this parameter super large, so it's forcing me to choose the smallest d that makes u really close to my desired feedback. Okay, so it's another way to write the quadratic program. And then the final thing are these three important photographs. You go on Stephen Boyd's website and you can download open source code for implementing QPs. It's very nice, CVXGen. And if you want to learn about these methods here, in ECE it's Nezhmiye, and in ME it's Ram. Okay, so two of our robotics faculty. They're spectacular. And then there's plenty of faculty in IOE who do this, though they're not so concerned with real-time issues and stuff like that. Okay, that's it for today. Tuesday is optional. I'm going to talk about the linear programming stuff. It'll only take about half an hour. And only come if you care about that. Otherwise, take the time to catch up on your projects and everything else. I know what end of school is all about. Okay, so thank you. Hey, thank you, thank you. A small amount of applause, but it's okay. It's been a good term so far.